Hi, physics. Mr. Janowski here. This is the third part of the Chapter 10 slides. So we've learned the basic stuff about the cousins. We've learned theta, we've learned omega, we've learned alpha, and we've learned the formula for arc length. And we're going to learn something new today that goes a little bit beyond this stuff. So let's get started. So, how do degrees relate to radians and revolutions? So, what is the little, I don't know, mathematical relationship that you're going to use to make field goal posts to get you out of one unit and into another? Use this one. 360 degrees is equal to 2 pi radians is equal to 1 revolution. So, what is the cousin of displacement x? The cousin of x is theta, also called angular displacement or just angle. And typically we're going to have that in units of radians, although degrees and revolutions are also units of angle. So what is the cousin of velocity, v? The cousin of v is omega, which is angular velocity, typically going to be in radians per second, sometimes in revs per minute. And what is the cousin of acceleration, a? The cousin of a is alpha, angular acceleration. So how is arc length related to angle? So what's your formula for arc length? It is S is equal to r theta, and this only works when theta is in units of radians. So what is your definition of velocity and your definition of angular velocity? So back to the idea of the cousins. Velocity is change in displacement over change in time, which means velocity's cousin, angular velocity, must be change in theta over change in time. And how about the definitions of acceleration and angular acceleration? Well, A is delta v over delta t, and that means its cousin alpha must be delta omega over delta t. If alpha is the cousin of A, then you want to replace this guy here with its cousin, which is this guy here. So yeah, remember the cousins. So question, can an object move with a constant speed and be accelerating at the same time? So think of that. The answer is yes, because speed is not the same thing as velocity. Acceleration is a change in velocity. So you can change your velocity by either changing the magnitude of your velocity, which is your speed, or the direction of your velocity, which is the direction, because velocity is a vector, or you can change both the magnitude and the direction. So if you're doing any one of these things, either changing magnitude or changing direction, or changing magnitude and direction, then you're accelerating. So if you have a point traveling in a circular path with a constant speed, which way is it accelerating? So focus on this point here at the top. So this guy at this moment has a tangential velocity to the right of the screen, but a moment later it's going to not be there, it's going to be here. And then a moment after that, it'll be here. So it's moving to the right. Which way is it accelerating? It is actually accelerating down. So this point's accelerating down. This point is accelerating up. If we had a point here, it would be accelerating this way to the left. A point here would be accelerating to the right. So any point along the outside of this spinning wheel is accelerating towards the center. And we call this centripetal acceleration. And I'm saying centripetal, not centrifugal. Those are different words. They mean different things. We'll get to centrifugal force later. But today we're just doing centripetal force and centripetal acceleration. So if you've got this object, so now this object is going counterclockwise around here. It's moving in a circular path, and it might have a constant velocity of just 6 meters per second, but it is constantly changing direction. And if your velocity is changing direction, then you are accelerating. That's what centripetal acceleration is. So the units of centripetal acceleration, here's your formula for centripetal acceleration, A sub c. It's v tangential squared divided by the radius. And the units of A sub c are meters per second squared. This is acceleration, so it's going to have the units of acceleration, meters per second squared. So don't mix these ideas up. Centripetal acceleration is not equal to angular acceleration. These are different ideas. Both of them have to do with objects moving in circles, but they mean very different things. So your formula for centripetal acceleration is tangential velocity squared divided by the radius, and your units will be meters per second squared. Your formula for angular acceleration, this is your basic definition for angular acceleration, alpha is delta omega over delta t. So change in angular velocity over change in time. So yeah, 4 years of teaching this stuff has taught me people love to get these ideas confused. And they love to get the units wrong, and they'll be thinking of one thing, and then they'll grab the other thing's formula. So make sure you're clear on the difference between these two things. Centripetal acceleration, this formula, meters per second squared. Angular acceleration, this formula, radians per second squared. And these guys are not cousins. So since v tangential is equal to r omega, as long as omega, your angular velocity, is in units of radians per whatever, radians per second squared. Radians per second, if we're doing it that way, we can use that to derive another expression. So this guy right here, this is our basic formula for centripetal acceleration. Well, if you sub in r omega for v tangential, and that gets squared, so both things get squared. So now we have r squared omega squared divided by r. Well, one of the r's cancels, and that gives you r omega squared. So this is another expression for a sub c, centripetal acceleration. So these are the two. I think of it first in this expression here, but this other one here, sometimes useful. So what is the centripetal acceleration of an object moving at 6 meters per second around a circle of radius 0.500 meters? So have we got a formula for centripetal acceleration? Yeah, we have two. We're going to use this one because we know 6 meters per second, this is the tangential velocity. This is not the angular velocity, this is tangential velocity, which is a meters per second kind of thing. That is, a type of velocity. And we know the radius, so that's our formula. We're going to plug in the things, put it in your calculator, and you will get centripetal acceleration is equal to 72 meters per second squared. So if that is our centripetal acceleration, and that's our radius, what is the angular velocity? So we'll do it the other way now. This time we know a sub c to start with, and we know the radius, so we're trying to get to the angular velocity, so why not use this formula? So start here, do the algebra, get the thing you want by itself on one side. You can't draw square roots, or at least not well, in Google Slides, so I raised it to the 1/2 power. That's the same thing. Plug in your numbers, and you will get 12 radians per second. So this is another one of those cases where if you looked at what was going on here, meters per second squared times meters, the meters part should have canceled out. You take this to the 1/2 power, we should just have something over seconds. But we needed radians to be there, so out of nowhere, radians magically appears. They're weird as a unit. So if the mass of this brick is 3.25 kilograms, and we're swinging it around at this tangential velocity in that radius, what force must the rope be providing to keep the brick moving that way? So how does force relate to mass and acceleration? Another way of saying this is, what's the most important thing you will learn in physics all year? That is F equals ma. In this case, we're talking about centripetal force, so F sub c is equal to ma sub c. So we'll use this equation. We'll just sub in, the formula for a sub c, plug in the numbers, and you get a centripetal force of 234 newtons. So we've got a mass moving in a circular path. It is constantly changing direction. So even though it's got a constant speed, its velocity is always changing because it's changing direction. That means it's accelerating. So there has to be a force. Newton's second law, F equals ma. If the thing is accelerating, there has to be a force. So we call that force the centripetal force. Centripetal forces are the things that provide centripetal acceleration. So start with, this is basically Newton's second law. And in this version, I replaced a sub c with one version of our formula for a sub c. A sub c is equal to v sub t squared over r. And in this bottom version, I replaced it with the other one because a sub c is also equal to r omega squared. So if you're driving your car and you're going around a turn, what is providing the centripetal force? Centripetal force in this case is going to be provided by the friction between your tires and the road. If there's no friction between your tires and the road, you can't turn your car because you need a force to change your direction because that's acceleration. So in this situation, this is often called a zero gravity ride, which is a very poor name because gravity is still there. It's not a zero gravity situation. But in this situation, what is providing the centripetal force? So it's easiest to see this guy here, the guy in the yellow shirt. So this thing's going around. I imagine if we're looking at it this way, it's going counterclockwise. So it's going around, which means at this moment in time, this guy had tangential velocity off in this direction. He would tend to fly off like this. But he's not going to. He is going to accelerate towards the center. So there must be a force providing that acceleration or causing that acceleration. That force is the centripetal force. And the thing that's causing that force is the normal force of the wall behind him that's pushing him forwards. So normal force in this case is the centripetal force. If that wall weren't there, the guy would fly off in this direction. So, related example. Imagine that we were all in the classroom. Wouldn't that be nice? And I was swinging a tennis ball on a string over my head. So we're looking at, this is the overhead view of what's going on here. So I'm swinging this tennis ball, around at a constant angular velocity. And the string is keeping it moving towards the center. So if all of a sudden I let go of that string is no longer providing that centripetal force. So which of these four paths is it going to follow? Is the ball going to keep going like this in path A? Is it going to fly off like this in path B? Is it going to fly off like this in path C? Or is it going to fly off this way, path D? One of these is correct, not a trick question. The correct answer is B. The ball is going to follow that path. So as long as the string is here, it's providing centripetal acceleration, and that's going to keep the ball going in this path. So at this moment, the ball has tangential velocity this way, but it is also accelerating this way because of the string. If all of a sudden I release the string, there's no longer that force providing centripetal, there's no longer that string providing centripetal force, which is causing centripetal acceleration. So if all of a sudden I lose that, suddenly there's no net force on the ball. So the ball was going in this direction. If there's no net force on it, it's going to go and in a straight line at a constant speed because that is Newton's first law. An object in motion will stay in motion in a straight line at a constant speed unless acted upon by an outside unbalanced force. But we just got rid of the outside unbalanced force. That was the string. So it's got to keep going straight line, constant speed. So quick review. When an object moves in a circular path at a constant angular velocity, which way is it accelerating? It will be accelerating towards the center. So that is centripetal acceleration. Is the answer to the next question. What do we call this kind of acceleration? Centripetal acceleration. What are the units of centripetal acceleration? Well, centripetal acceleration is acceleration, so its units will be meters per second squared, because it is in fact acceleration. So what is the difference between centripetal acceleration and angular acceleration? So centripetal acceleration is its regular acceleration. It's towards the center. It has the units of regular acceleration, meters per second squared. Angular acceleration is the change in the angular velocity divided by the change in time. So it is the rate with respect to time at which the angular velocity is changing. If you know the calculus, it's not delta omega delta t. It would actually be d omega dt. Derivatives, don't worry about that. Ask Mr. Babias about that. But anyhow, angular acceleration has units of radians per second squared. So different kind of thing. Again, experience has taught me that students love to mix these ideas up. So make sure you're clear on the difference between these two. And that's it for these slides. So hopefully you found that helpful.